This is stochastic processes, Mod-08 renewal processes. In the first two lectures, we have discussed renewal functions and its properties, and then we have discussed renewal theorems. There are three important theorems we have discussed in the lecture 2. Today's lecture is lecture 3, Markov Renewal and Markov Regenerative processes. In this lecture, I am going to cover Markov Renewal process or semi-Markov process, the definition and its properties. Followed by the definition and the properties, I am going to discuss the steady state measures, and I am going to discuss one simple example for the semi-Markov process. Then the second part of today's lecture, I am going to cover Markov Regenerative process. The definition and the properties I am going to discuss, followed by the definition and the properties, I am going to discuss the limiting distribution. As an example, we are going to discuss the steady state analysis of GM1N Q. First, we are going to discuss the various stochastic processes which consist of DTMC, CTMC, semi-Markov process and Markov regenerative process. First, you consider number 1, the sojourn times are exponential distribution. Number 2, every state change represents a regeneration instant. The epochs or points T1, T2 and so on, in which the process probabilistically restarts from scratch, that is, from epoch T1 the process is independent of its past, and the stochastic process behavior from epoch T1 is the same as it had from T0 is equal to 0. These epochs or points are called regenerative epochs or regenerative time points or regenerative instants. So, these are all the two important properties. One is the sojourn times are exponential distribution. The second one is every state change represents the regeneration instant. Accordingly, we can classify the stochastic process. The first one is if both the properties are satisfied, then the corresponding stochastic process are either it is a Markov process. So, based on the time space is a discrete or continuous, we have a discrete time Markov chain or continuous time Markov chain. Whenever the two properties are satisfied, the stochastic process is said to be a Markov process, and the state space is a discrete, then the Markov process is called a Markov chain, and based on the time space or parameter space is a discrete or continuous, accordingly we have a discrete time Markov chain or continuous time Markov chain. If any stochastic process satisfies the property number 2 only, not the property number 1, that means the sojourn times are exponential distribution. If that property is not satisfied, then that stochastic process is called a semi-Markov process. We are going to discuss in detail about the semi-Markov process, that is a stochastic process satisfying the property number 2 only. If both the properties are not satisfied, but still not every state change represents the regeneration instant, instead of this there are few state change represents a regeneration instant, then the stochastic process is called a Markov regenerative process. So, if two properties are satisfied, then it is a CTMC or DTMC. If only the property number 2 satisfies, then it is a SMP. If both the properties are not satisfied, but few state change represent a regeneration instant, then the stochastic process is called a Markov regenerative process. So that we have shown it in the diagram. From the stochastic, from the semi-Markov process, you can have an embedded DTMC by making a proper assumptions that the sojourn times are exponential distribution, then it will be a CTMC. From the CTMC, you can create the DTMC in the embedded. Similarly, from the SMP, you can make a embedded DTMC. By proper assumptions, you can get the DTMC or CTMC. The general case of a semi-Markov process is a Markov regenerative process. If you make some assumptions, then it will be a semi-Markov process. The down arrow means if you make additional assumptions in the Markov regenerative process, then you will get the semi-Markov process. If you make additional assumptions in the semi-Markov process, then you will get a DTMC or CTMC. Whereas these dotted arrows means embedded stochastic process. So from the DTMC, from the CTMC, you can have a embedded DTMC. From the SMP, you can have a embedded DTMC. From the MRGP, you can have a embedded SMP. And from the SMP, you can have a embedded DTMC. So this is a pictorial representation of a various stochastic process based on these two properties. Now we are moving into the semi-Markov process introduction. Consider a system Yt with the state space omega. That means the Yt is a discrete state continuous time stochastic process. Suppose that the system is initially in the state x0 at time t0. It stays there for a non-negative random amount of time, which may follow a general distribution, and then the system jumps to the state x1 at the next transition time instant t1. It stays there for non-negative random amount of time and then jumps to the state x2 at the next transition time instant t2, and the process continues like this. Thus, xn is the nth state visited by the state system at the time instant of nth transition tn. This can be depicted through the sample path. So, sample path means it's a trace. Consider this sample path of semi-Markov process. The corresponding Yt is in the y-axis. The time is in the x-axis. Y-axis is y of t. The corresponding stochastic process has the 4 states. Omega is 1, 2, 3, 4. So at time 0, the system is in the state 1, and the system is in the state 1 till time t1 time instant. At the time t1 instant, the system moved to the state 2. So the system was in the state 0 at time t0, that is equal to 0, and at the time t1 it moved to the state 2. The system is in the state 2 till time instant t2, and then it moves to the state 3 at time instant t2. So from the state 2, the system moves to the state 3 at the time point t3. T2. The system moves to the state 4 at the time instant T3. Now the system is in the state 4, and the system was in the state 4 till the time point T4, then it moved to the state 1 and so on. And the T1, T2, T3, T4 are the time instant. In those time instant, the system is moved from one state to the other states. Go back to the previous slide. The system was in the state x0 at time t0, and at time t1 the system moved to the state x1 and so on. Thus, xn is the nth state visited by the system at the time instant of nth time transition Tn. So, in this sample path, T1, T2, T3, T4, T5 are the time instants, and the system is visiting the states. So, here it is a 4-state model. The omega is 1, 2, 3, 4. Therefore, the system is keep moving into the from one state to other states according to this state transition diagram. We will come back to the same example again. So, this is an illustration of a sample path of semi-Markov process, and the T1, T2 are the time instant. If Yt denotes the system, if Yt denotes the state of the system at time t, then Y of Tn is equal to Xn. Whenever you observe at the time instant the system, then that is the possible values of Xn. If the Markov property is satisfied at all the transition time instants Tn, then the stochastic process described above is called the semi-Markov process. Whenever the Markov process is satisfied at the time instant T0, T1, T2, T3, T4 and so on, all the time instants. The time instants are nothing but the system is moving from one state to another state at those time instants. So, if the Markov property is satisfied at these time instants, then the stochastic process Y of t is called the semi-Markov process, or in other words it is called the Markov Renewal process. That is, the evaluation of the system after the time instant t equal to Tn depends only on the past history of the system till the time Tn. In other words, if Yt is a semi-Markov process, then the process at Y of t plus Tn is independent of. A semi-Markov process is thus a stochastic process in which changes of state occur according to a Markov chain, and in which the time interval between two successive transitions is a random variable whose distribution may depend on the state from which the transition takes place as well as on the state to which the next transition takes place. Y of t. Y of t plus Tn is independent of Y of t given the complete past history Y of t, and Xn is equal to I, and is identical to the process Y of t given x0 is equal to I because of time homogeneity. Not only Y of t plus Tn is independent of Y of t, it is also identical to the process Y of t given x0 is equal to I because of time homogeneity. It is satisfying the time invariant property also. So, it is very important, when the Markov property is satisfied at the time in transition time instance Tn, then the stochastic process is called a semi-Markov process. Thus, In a semi-Markov process, the Markov property is satisfied only at each of the transition epochs and not at all times. This is very important. The Markov property is satisfied only at each of the transition epochs Tn, not at all the times. If the Markov property is satisfied at all times, then the stochastic process is called the Markov process. Since it satisfies only at each of the time transition instance, the Markov process is called a semi-Markov process. The fact that the Markov property holds at each of the transition epochs Tn of the stochastic process y of t entails the Markov property also holds for xn. Since xn is nothing but the y of Tn, therefore the Markov property is satisfied for the stochastic process xn, not for the Markov property is satisfied for the y of t for all times. Hence, xn turns out to be the time homogeneous embedded Markov chain with the state space omega. Y of t is a stochastic process and x of n is nothing but the y of Tn, where Tn is the transition time instance, and the Markov property is satisfied only at all the transition time instance. Therefore, xn form a discrete time Markov chain. Since xn is y of Tn, this xn stochastic process is called a embedded Markov chain. Xn stochastic process is embedded in the stochastic process y of t. Therefore, xn is a time homogeneous embedded Markov chain because it satisfies the time invariant property as well as the Markov property. Therefore, xn is the time homogeneous embedded discrete time Markov chain. Now, we can say x of n comma t of n constitute a Markov renewal process or semi-Markov process with the state space omega. Xn is a embedded Markov chain where xn is y of Tn and the Tn is nothing but the transition time instance. Therefore, the together xn comma yn constitutes Markov renewal process because these are all the time points in which the system is moving into the different states, and the Markov property is satisfied only at those time points. Therefore, it is called the semi-Markov process or Markov renewal process with the state space omega. The stochastic process y of t is not a Markov process, although it inherits some important properties of Markov processes. The associated process, that is x of n, is a Markov process. Hence, the name xn comma tn as a semi-Markov process. In conclusion, a continuous time stochastic process in which the embedded jump chain, that is nothing but the discrete process, registered what values the process takes. So, the embedded jump chain is a Markov chain In conclusion, a continuous time stochastic process which embedded has a Markov chain and where the holding times are random variables with any general distribution whose distribution function may depend on the two states between which the move is made, we say it is semi-Markov process or Markov renewal process. Whenever these properties are satisfied, we say the stochastic process is a semi-Markov process or Markov renewal process. The semi-Markov processes are non-Poissonian with the renewal property. This means that the probability of a jump from a state I to j at a certain time depends only on the states I, j and the time t since the last jump occurred. If you restrict the holding times or exponential distribution and each time transition instance or the renewals, then the special case of the semi-Markov process is a Poisson process. But in general, semi-Markov processes are non-Poissonian. If you make assumptions of holding times or exponential distribution with the same parameter and each time transitions are nothing but the renewals, then the special case of semi-Markov process is the Poisson process. A semi-Markov process where all the holding times are exponential distribution is called a continuous time Markov chain. So, if I restrict only the holding times are exponential distribution, the each transition need not be the renewals, then a semi-Markov process is a continuous time Markov chain. Now, we are going to discuss the steady state measures of semi-Markov process. The analysis of a semi-Markov process is performed in two stages. In the first stage, the semi-Markov process stays in a state I for some random amount of time. For example, in the sample path of a semi-Markov process, in this model we have a 4-state semi-Markov process. So, in each state the system stays a random amount of time. Let us consider that the time spent in state I follow a general distribution with the distribution function hi of t. That means in this example h1 of t, that is the time spent in this system spent in the state 1. h2 of t is the distribution of the system staying in the state 2 and so on. In the second stage, the SMP moves from the state I to j with the probability pi, j, where pij is defined. What is the probability that the system was in the state I at the nth time instance? The system will be in the state j at the n plus 1th time instant, I, j belonging to omega. So, that is a conditional probability. The conditional probability of p x n plus 1 is equal to j given x n is equal to I for I, j belonging to omega. So, the SMP can now be completely described by the vector of sojourn time distributions h of t and the transition probability matrix P, that is P of I, j. So, the transition probability matrix is the transition probability, therefore, all the row sums are equal to be 1 and the values are lies between 0 to 1. And you have to supply the sojourn time distribution for each state. So, if these two informations are given, then we are known with semi-Markov process. To compute the steady state probability vector, let us assume that pi is the vector, pi 1, pi 2 are the elements of a semi-Markov process. First, calculate the mean sojourn time. That is nothing but the small hi. Since hi of t is the distribution function, so 1 minus hi of t, the integration between 0 to infinity will be the mean sojourn time, because each random variable is a non-negative random variable, therefore the mean will be 0 to infinity 1 minus the CDF integration for each state I. Next, find the steady state probability vector Vi's for the embedded Markov chain of the semi-Markov process. First we have to find out the steady state probability vector for the embedded Markov chain of the semi-Markov process, and using the steady state probability vector and the mean sojourn time, you can get this steady state probability vector of pi. So how to find the steady state probability vector of embedded Markov chain? So you know P is a transition probability matrix. So solve V is equal to Vp and summation of Vi is equal to 1, you will get Vi's. The V is equal to Vp is a homogeneous equation, and including summation of Va is equal to 1, you will have a non-homogeneous system of equation. So you can get the non-trivial solutions satisfying these two conditions. So once you know the Vi's, you can compute the steady state probabilities of the semi-Markov process. That is nothing but Vi's multiplied by Hi's divided by summation of all the Vj's Hj's, where J is belonging to omega. So the Vi's are nothing but the steady state probability vector of embedded Markov chain, and Hi's are nothing but the mean sojourn time, and the pi i's you will get by using this formula. Now let us consider the simple example, the stochastic process with the state space omega 1, 2, 3, 4. In the previous steady state measures, with the assumption that the steady state probabilities exist, we are giving the how to compute the steady state probability measures. So here the assumption is that steady state probabilities are exist. Now we come to the example. So this is a 4-state stochastic process with the states 1, 2, 3, 4, and H's are nothing but the CDF of sojourn time in each state, and xn is nothing but y of tn, and xn comma tn will form a Markov renewal process or semi-Markov process. Assume that the time spent in the states 1 and 2 follow exponential distributions with the CDF h1 and h2, whereas the time spent in the states 3 and 4 follow uniform distribution with the CDF h3 of t and h4 of t. So the sojourn time in the state 3 is uniformly distributed between the intervals 1 and 2, and the sojourn time spent in the state 4 is also uniform distribution between the intervals 2 and 3. Therefore, the CDFs are in this form h3 of t and h4 of t. The semi-Markov process moves from the state I to j with the probability Pi of j, that is nothing but the transition probability matrix can be in the form the states are 1, 2, 3, 4. Therefore, in the one-step transition probability of system is moving from 1 to the state 2 is sure, therefore that probability is 1 and all other probabilities are zeros. Similarly, the system moved from the state 2 to 3, that probability will be 1 and all other states moving probabilities are 0. Therefore, all other transition probabilities from the state 2 to 1, 2 to 4 are 0, whereas the 2 to 3 will be 1. Similarly, 3 to 4 will be 1 and all other states, all other transition probabilities are zeros. Then the system moving from the state 4 to 1 is 1 and all other states are 0. So, you know the transition probability matrix as well as you know the the Sojourn time distribution. So, using the transition probability matrix, by solving you can get the steady state probability vector of embedded Markov chain. If you see the transition probability matrix, since it is a transition probability matrix, the values are lies between 0 to 1 and the row sum is 1. But in this particular transition probability matrix, it satisfies the one more additional condition, the column sum is also 1. Therefore, if you solve the V is equal to Vp and the summation of Va is equal to 1, the solution will be 1 divided by the number of states. So, the steady state probabilities are uniformly distributed, uniform distribution. So, number of states are 4, therefore, the steady state probability of the embedded Markov chain is 1 by 4. So, you know the steady state probabilities of embedded Markov chain, and from the Sojourn time distribution you can find out the mean sojourn time. Since the first two random variables first two states sojourn times are exponential distribution, therefore, the mean sojourn time is 1 by 2, 1 by 3 respectively for the states 1 and 2. And the sojourn time in the state 3 is uniform distribution between the interval 1 to 2. Therefore, the mean sojourn time is 3 by 2. And for the state 4, the sojourn time distribution is uniform distribution between the intervals 2 to 3. Therefore, the mean sojourn time is 5 by 2. So, using transition probability, using the steady state probabilities of embedded Markov chain and the mean sojourn time, using the steady state probabilities of embedded Markov chain and the mean sojourn time times, you can get the steady state probabilities of semi Markov process. Finally, compute the steady state probabilities of semi Markov process using VIs and HIs. VIs are 1 by 4 and HIs are H1 is 1 by 2, H2 is 1 by 3, H3 is 3 by 2, H4 is 5 by 2. You substitute the values in this equation to get the steady state probabilities of semi Markov process. Now, we are moving into the second part of lecture 3, that is Markov regenerative process. Consider a stochastic process Z of t with the state space omega. Suppose that every time a certain phenomena occurs, the future of the process Z, that means Z of t, after that time becomes a probabilistic replica of the future after time 0. Such times usually random, are called regeneration times of the stochastic process Z of t, and the process Z of t is then said to be regenerative. Such a process is called a regenerative process. We consider a stochastic process wherein there exists a time points where the process satisfies the memoryless property. These time points are referred to as a regeneration points. In a Markov regenerative process, The stochastic evaluation between two successive regeneration points depends only on the state at regeneration, not on the evaluation before regeneration. Furthermore, due to the time homogeneity of the embedded Markov renewal process, the evaluation of the Markov regenerative process becomes a probabilistic replica after each regeneration because of time homogeneity, time invariant. As a consequence, all memory other than the state must be reset at the regeneration point. As a consequence, all memory other than the state, that means the future depends on the state but not the past history. AD property of inter-arrival time is making arrival instance independent and hence memoryless as the next arrival does not depend on how long the previous arrival took. Also, since between any two arrivals same pure depth process operates, hence the arrival points become regeneration time points, must be reset at a regeneration point. Now, we are going to consider the sample path of a Markov regenerative process. Through that, I am going to explain the regeneration points. Consider the sample path of a Markov regenerative process. In this stochastic process, the omega is 0, 1 and 2. Consider the simple example of a G M 1 2 queuing model. That means the arrival is a non-Poisson process. That means the inter-arrival time distributions are not an exponential distribution, whereas the service times are exponential distribution. Only one server and the capacity of the system is 2. Therefore, the state transition diagram is like this. This is a CDF of the system spending in the state 0 before moving into the state 1. The system spending in the state 1 before moving into the state 2, the CDF will be f of t. Because the capacity of the system is 2, there is a possibility the arrival can come, but the system will be in the state 2 again. Therefore, I made a self loop with the dotted arcs. Whereas, if the service is completed with the assumption of a service is exponential distribution with the parameter mu, then the system can move from the state 2 to 1, 1 to 0 also the rate will be mu. So, now you see the sample path. At time 0, the system is in the state 0. The inter-arrival time is any distribution, need not be an exponential distribution. At time S1, at time instant S1, the first arrival enter into the system. Therefore, the system size is now 1. So, system move to the state 1. Now, there are two possibilities. Either the service would have been completed before the next arrival, or the next arrival occurs first before the service completion of the first arrival. server first customer who is under service. So, suppose you assume that second arrival occurs first before the completion of the service completion of the first customer. Therefore, system move to the state 2 at the time point S2. Now, consider the scenario. The first customer who is under service, his service completed first before the third arrival. Therefore, the system size now it will be 1. That means earlier the system was in the state 2. Since the service is completed, the system size becomes 1 for some time. At this duration, the third customer enter into the system at the time point S3. Now the system size is 2 again. That means initially the system state was 0. From state 0, the system moved to the state 1 because of f of t. Then one more arrival, therefore system size 2. First customer service completion, system state is 1. Then the third arrival, now the system state is 2. Then the service completion, therefore it goes to the 1. One more service completion, therefore the system goes to the state 0. Then the arrival S4. Note the time points S1, S2, S3, S4. These are all the time points in which the arrival occurs. That is nothing but the arrival epochs. Whereas this is a time point in which the service completes. This is a time point in which the service completes. This is a time point in which the service completes. We are not noting down the service completion time points, whereas we are note down the arrival time epochs, because at the time of service completion epochs, still we should know how much elapsed time of the next arrival, because inter arrivals are now it is any distribution, not an exponential distribution. If it is exponential distribution, then the memoryless property is satisfied. Therefore, the residual or the elapsed or the remaining inter-arrival time is also exponential if inter-arrival times are exponential distribution. But here therefore, at the time of service completion, we should remember the elapsed or remaining inter-arrival time. Therefore, at the service completion time epochs, the memoryless property won't be satisfied. Whereas, at the time instance S1, S2, S3, S4 and so on, these are all the time points in which the arrival occurs. At those time points, the memoryless property satisfied. Even though the system is moving into the different states in between the arrival time epochs. For instance, between the time epochs S2 to S3, the system is moved from the state 2 to 1. At the time point 2, at the time point S2, the system was in the state 2, whereas at the time point S3 also the system is in the state 2, but in between the system was in the state 1 for some time. Similarly, in between the time instance S3 and S4, the system was in the different states in between these two time epochs. And in between, even though the transition occurs at those time points, the memoryless property was not satisfied, whereas at the arrival time epochs, the memoryless properties are satisfied. Therefore, these time points are called Go back to the definition. The stochastic process where there exists a time points where the process satisfies the memoryless property. The time points are referred as a regeneration time points. So, here the S1, S2, S3, S4 are the regeneration time points. In a Markov regenerative process, the stochastic evaluation between two successive regeneration time points, that means between S2 to S3 or S3 to S4, it depends only on the state at the transition and at regeneration, not on the evaluation before regeneration. That means you should remember where the system was at the time point S2 as well as where the system was in the state at the time point S3, and you do not want before the regeneration time. As a consequence, all memory other than the state must be reset at the regeneration point. Therefore, this stochastic process is called a Markov regenerative process, and I have made a sample path for a Markov regenerative process with this example, because we are going to consider the same example later. So, here S1, S2, S3 are the regeneration time points, not the time instants at which the service completion. The concept of MRGP are given in next two definitions. The first definition, a sequence of bivariate random variables yn, Sn is called a Markov renewal sequence or Markov renewal process. S0 is equal to 0. In this example also we made it S0 is equal to 0. Sn plus 1 is greater than or equal to Sn, and Yn is belonging to omega dash, where omega is the state space, omega dash is the subset of omega. For all n greater than or equal to 0, the Yn, the conditional distribution of Yn has to satisfy this property. The first line, the probability of Yn plus 1 is equal to j with the difference of time instants is less than or equal to t, given that the system was in the state, some state at y0 at the time instant S0 till the system was in the state I at the time instant Sn. This conditional distribution is same as the conditional distribution with the only the latest information. The probability of Yn plus 1 is equal to j, the difference of regeneration time points is less than or equal to t, given only Yn is equal to I. That means the conditional distribution depends only the current information or latest information, not the complete history. So, that is nothing but the Markov property. Next, that is same as the conditional distribution of instead of Yn to Yn plus 1, you can find out the distribution of Y0 to Y1. Because of it is a time invariant, because of it is a time homogeneity, this conditional distribution is same as probability of Yn is equal to j, the first regeneration time point is less than or equal to t, given that Y0 is equal to I. So, that means the conditional distribution depends on the current state, not the past history, including the time homogeneous property. Then that is the way we define the bivariate random variables, that is Yn, Sn satisfies this property. Then the MRGP is defined as follows. A stochastic process Z of t with the state space omega is called a Markov regenerative process. If there exists a Markov renewal sequence yn comma Sn such that all conditional finite dimensional distribution of z of Sn plus t given z of u, where u is lies between 0 to Sn, yn is equal to I, are the same as those of z of t given y naught is equal to I. So, this is the probabilistic replica. The stochastic process z of t is said to be a Markov regenerative process if all conditional finite dimensional distribution of z of Sn plus t given all the past history till Sn including yn is equal to I, that is same as the distribution of z of t given y naught is equal to I. That means it includes the time homogeneity as well as the Markov property. Note that the above definition implies that z of Sn plus n plus or z of Sn minus is a embedded discrete time Markov chain or just a embedded Markov chain in z of t. Also, Sn is the stopping time or regeneration points. Stopping time is nothing but the Markov property is satisfied at those time points for the given stochastic process. So, in this example, before the arrival occurs, z of Sn minus is a embedded discrete time Markov chain just before the arrival occurs. Will be a embedded Markov chain in this example. The way we discuss the semi-Markov process with the transition probability matrix and the Sojourn time distribution, here we have to explain the global kernel and the local kernel. So, that we are going to discuss now. We denote the conditional probability in the equation number 2 by k I of j of t. Equation number 2 is nothing but the conditional distribution of yn plus 1 is equal to j with the difference of time in time regeneration times are less than or equal to t, that is same as because of Markov property and the time homogeneous property, this is the probability of yn is equal to j, comma s1 is less than or equal to t given y naught is equal to I. A Markov renewal sequence is also defined in the bivariate as this, and usually this form of definition is frequently used since renewal time and the state of the time and the state of the system at renewal instant both are important. So, this conditional probability becomes the transition probability, that is this conditional probability will form a matrix k of t, and that is called a global kernel of the Markov renewal sequence. For the Markov renewal sequence, we can find the global kernel, and the global kernel is the matrix k of t that consists of k of I comma j of t, where each k I comma j of t is nothing but probability that p of y1 is equal to j with s1 is less than or equal to t given y naught is equal to I. Now, we are going to discuss the local kernel, that is also a matrix that consists of E of I comma j of t, where I is belonging to omega dash and j is belonging to omega. Omega dash means the collection of states at which the the time transitions of the system satisfies the Markov property at those time instants, those collection of states forms a omega dash, and that is a subset of omega. So E of I comma j of t is nothing but what is the probability that the system will be in the state j with the first regeneration time point is going to be greater than t. That means the system will be in the state j after the time t. The first regeneration going to occur after time t. The system will be in the state j at the time t, given it was in the state I at the previous regeneration time point, or at S0 the system was in the state I. So this will form a local kernel. So using global kernel and the local kernel, one can find the steady state and the transient behavior of Markov regenerative process. Now we are going to discuss the limiting distribution or steady state measures. We study the limiting behavior of the MRGP by taking limit as a t approaches infinity. We require two new variables to be defined, namely the mean time alpha I comma j of the MRGP spends in the state j between two successive regeneration time instants, given that it started in the state I after the last regeneration. So this is nothing but the average spending time in the state j, given that it was in the state I at the last regeneration. So alpha of I comma j is nothing but the expectation of a time in state j during the interval 0 to S1, where S1 is the first regeneration time instant, given that the system was in the state I at the previous or last regeneration time. And the steady state probability vector V of the embedded Markov chain. That means V is equal to Vp and the summation of Vk's are is equal to 1, where k is belonging to omega dash, and the P is the one step transition probability matrix of embedded Markov chain. So from the global kernel k, that is a k of t. If you make a t tends to infinity, you will get the one step transition probability matrix P. So from using P, you can get the steady state probabilities V by solving V is equal to Vp and the summation of Vk is equal to 1. Once you solve this using the alpha ij, you can get the limiting distribution. So the limiting distribution is given in the following theorem. Let z of t be the MRGP with the Markov renewal sequence yn comma Sn. Let nt denotes the total number of states changes by time t. Then the sample path of zd are right continuous with the left limits, and the n of t is a semi-Markov process. The y of n of t is a semi-Markov process which is irreducible, aperiodic and positive recurrent, and V is a positive solution to the equation 4, that is this one, summation of Vi is equal to 1 and V is equal to Vp. If these properties are satisfied, then the steady state probability vector pi, whose elements are pi j's, that is nothing but the limit t tends to infinity, probability of z of t is equal to j, using this formula where bk's are nothing but the summation of alpha k's. So as long as these three properties are satisfied, that means the sample path has to be right continuous, and the semi-Markov process has to be irreducible, aperiodic and a positive recurrent, and you need a positive solution, the steady state probability vector, then you can get the steady state probability for the Markov regenerative process